So welcome everybody to today's session of the Cardiff Analysis Seminar. So today we are still online. Next week we'll be in person. We are delighted to have Giovanni Alberti from the University of Genova, who will be talking about regularity theory for Maxwell's equation. So thank you very much for accepting our invitation. So we're very happy to have you here, and over to you.
Yeah, thanks a lot for the introduction and for the invitation. I'm very glad to be able to give this online talk at Cardiff. So this talk is like a general overview of the regularity theory for Maxwell's equations. So hopefully it's gonna be mostly based on ideas rather than on precise technicalities that are very frequent in analysis, unfortunately. So it's basically just a collection of techniques that are used for proving regularity theorems for Maxwell's equations. So let me go straight to the problem. We are going to focus on these PDEs, Maxwell's equations in their time harmonic form. So basically after taking a Fourier transform somehow, here time is replaced by frequency. So the frequency omega here. And this, of course, these PDEs appear in many different physical modeling. I'm not gonna mention anything on those aspects. I'm just taking them as a known datum, let's say. So these are Maxwell's equations, and here omega is a bounded domain in R3, E is the electric field, H is the magnetic field. And these are the solutions. These are the boundary conditions. At the beginning of this talk, we'll forget them basically, and we'll just recall them at the end. So as I was mentioning, E and H are the electric and magnetic fields. In principle, they may not be in H1, which is the typical, let's say, space where weak solutions to elliptic PDEs are looked for. Here, E and H are only in H curl. Namely, it means that E and H are in L2 and their curl is in L2 as well. So we require not the full gradient to be in L2, but only the curl. So what are the main regularity questions that one can ask? The first one is when E and H are actually in H1. So when the full gradient of E and H is in L2. This, as I mentioned before, this for elliptic PDE, this is a free property. In this case, it's not free. It doesn't come for free. It has to be proven under some assumptions. So that's the one of the main property one wants, that you can take a gradient basically. The second one is not taking gradients, but taking pointwise values. To take pointwise values, you need some sort of continuity of E and H, and in PDE settings, usually continuity is measured in Hölder spaces. So we ask ourselves when E and H are in C0 alpha. And then, of course, there are the corresponding higher regularity properties. So when E and H are in HK or in CK alpha, and these will be just somehow a consequence of the first two results, exactly as in the classical elliptic or hyperbolic or parabolic cases. And then, of course, one may also ask other additional questions, and I will mention some of them during my talk. So this will be just, I'll try to be as basic as possible. So I will just touch upon many of these results that you see in this list of references. Just to keep the presentation as direct as possible, I will avoid mentioning the specific points where I use this or that paper. So this is a list of references. You can find them here. I can share the PDF, no problem. But you will not see them again in the slides. Some of the recent results on this topic, you can find them in this book, which contains some kind of general discussion, and some of the C0 alpha estimates are in this paper here. Right, so the talk is outlined. The outline of the talk is as follows. We start from interior regularity, so we stay away from the boundary to avoid boundary effects. Then the second part is on global regularity, so how to deal with the presence of the boundary. And at the end, I will just spend one slide to discuss what doesn't fit in this somehow in what I discussed before. So let's start from interior regularity. So here again are Maxwell's equations, and we consider the regularity of the solutions in a compact set inside omega. So basically we stay away from the boundary. For compactness of notation, this coefficient here, omega epsilon plus I sigma, I call it gamma. I will come back to the precise definitions on epsilon, sigma, and mu. So far, they are just functions. And as I said, I'll come back to this later. So let me just warm up a little bit so that we understand what kind of problems we face when studying this type of regularity theorems. So let's consider the limit as the frequency goes to 0. This is the low frequency limit in Maxwell's equations. As you will see in a second, this is a very well-known situation. So let's see what happens. So if we put omega equal to 0 here, a bunch of terms disappear completely, and so that's what you get. Now, first thing, E is curve-free. So this means that it has a scalar potential. So E is a gradient being curve-free, supposing that you don't have topological problems. But since this is a regularity proper, we are looking for regularity properties. These are local properties. So somehow topological problems, we avoid them. So we suppose we live in a ball, for example. So in a ball, certainly, if you have a curve-free vector field, it has a scalar potential QE. And so E is a gradient. But then I can insert this expression here in the second equation, and I take a divergence. The divergence kills my curl, the curl of H, and I'm just left with this equation here. And this is just the conductivity equation for the electric potential. So this is basically in the conductivity setting, the conductivity regime. And for this type of PDE, this is a standard elliptic PDE. Regularity is super easy to achieve because, for example, if we want H2 type regularity, it's enough for the coefficient to be in W13. This is standard elliptic regularity. The solution becomes in H2. And then if QE is in H2, automatically its gradient is in H1. And so E is in H1. And so basically our first regularity question is easily solved. Similarly for the C0 alpha question, because as soon as sigma is C0 alpha, then again, by elliptic regularity, the solution to this equation is C1 alpha. These are the so-called Schauder estimates. And if QE is C1 alpha, you take a gradient, E becomes C0 alpha. So you see that in this omega equal to 0 case, those properties are very easily satisfied. Then, of course, since elliptic regularity has higher regularity results, you get automatically higher regularity estimates as well, and possibly additional, sorry, there's something wrong here.
Sorry, Giovanni.
Yes.
Can I ask a question? You're assuming here that there are no regions of zero conductivity.
Yes, sorry. This is something I haven't mentioned yet. In a couple of slides, I will mention assumptions on sigma and epsilon, and here you will see that I assume global ellipticity. So those matrices will be coercive. So no problems of ill-posedness of the PDE, let's say. Yeah, sorry. The second warm-up is to consider a case where I don't have the zero frequency, so omega may not be zero, but I consider homogeneous isotropic media. So this means that my two coefficients are constant and scalar. So this is an easy setting, but let's see whether in this also simplified scenario, I can say something. So in this case, I suppose that the sources are in H div, which means that their divergences need to be in L2 as well. So let's see what happens here. So the key observation here is that, again, you take a divergence in the first equation. And since gamma 0 is constant and isotropic, I can take it out from the divergence and put it on the other side. So the divergence of E is simply this thing here, which is a multiple of the divergence of JE. And so in particular is in L2 because the divergence of JE was in L2. The curl of E, this is for free because in the second equation, the curl of E was already in L2. And so basically I have a vector field E whose divergence and curl are in L2. So can I say from this that also the gradient is in L2, namely E is in H1? So does do the divergence and the curl give me something on the full gradient? And the answer is yes. And this is the so-called Gaffney-Friedrichs inequality. This is a simplified statement without the boundary. And this is simply saying that if you are in H curl and in H div, you're also in H1. So curl and divergence control the gradient, which is exactly what we need here. Why does this hold? Well, first thing, you use a Helmholtz decomposition. So in this case, you are not in the curl-free setting. So we cannot say that F is only a gradient. We have to add a curl part. which is this part here. So as I said, we ignore topological problems. So every time I can always do this Helmholtz decomposition. So I can write any vector field as a sum of a curve-free part and the divergence-free part in this way here. And then what do I do? Well, let me take another curl in this equation here. The curl of the gradient disappears. So I have the curl of phi, which on the one hand is equal to curl of f because of this equation. And on the other hand is equal to the Laplacian of phi because phi is divergence free. And then I have an elliptic PDE for phi. And here you see, this is a very nice elliptic PDE, and automatically I get phi in H2 because curl of f is in L2 by assumption. All right, so the phi part is easy. Now I have, and so if phi is in H2, then the curl of phi is in H1. And note that then this means that this bit here of f is in H1. So that's one part of the job is done. We are left with the gradient of Q. And here, instead of taking the curl, I take a divergence. If I take a divergence of this identity here, divergence of curl disappears. And so I get Laplacian of Q, which is a divergence of the gradient of Q, equals divergence of f. Again, exactly an equation like the one before. The divergence of f by assumption is in L2. And so I get, as before, Q in H2, and therefore gradient of Q in H1. So if you combine these two lines, you see that f is in H1 as well. So basically, this is a short proof of this famous and well-known inequality. And basically, this solves completely the constant and homogeneous and isotropic case. So basically, now the idea will be to combine these ideas, on the one hand, using this type of Helmholtz decomposition to reduce to elliptic equations, which was basically the topic of this warm-up 2. And recall also that in the warm-up 1, we obtained some kind of PDEs where, again, we had elliptic PDEs, non-constant coefficients, but somehow the non-constant coefficient here, even if it was a matrix, we could deal with it very easily by using elliptic regularity again. So the idea is just to combine all these ideas together in the general setting. So let's see how to do this. And before doing that, let's go through quickly the assumptions we make. So the first assumption is just the frequency omega. This is just a positive number. So this is easy. Then we assume that all the coefficients here, so epsilon, sigma, and mu, are matrices, bounded, and elliptic. And elliptic means that, as I was mentioning before to Marco, they are coercive. So they satisfy uniform ellipticity condition in the whole domain omega. All right, so we do not have the degenerate conditions here. And finally, I suppose the sources in the general setup to be just in L2. Then I will add assumptions as needed, as I did before. But so for the general weak formulation, JE and JM can just be in L2. All right, so let's see the first result. The first result is in H1 regularity. Now I don't see the screen well. I don't know if you see it well or not. Right, now it's okay. So here I'm just repeating the PDEs for Maxwell's equations, and the theorem is as follows. It is enough, exactly as we saw in the zero frequency case, to require the coefficients to be in W1 free and the sources to be in H-diff to obtain E and H in H1. So basically we see here that the situation is exactly the same as the one we saw in the zero frequency case with the conductivity equation, exactly the same result. Let's see why this holds. So for simplicity, I just take the coefficients to be in W1 infinity, because otherwise the proof becomes a little bit more technical, but somehow the ideas and the techniques are exactly the same. So let's see how this works. So first step, as we did in the Friedrichs inequality, let's use the Helmholtz decomposition of the two fields E and H. So both E and H, I decompose them with a scalar and vector potential. So exactly in this form here. Now I want to use elliptic regularity applied to the vector and scalar potential. So to QE, phi E, QH, and phi H. So first of all, what are the equations satisfied by the vector potentials phi? Well, here you see, you just apply another curl here in these equations here. Now you observe that the curl, no, sorry, I made a mistake. You take the first equation here, the curl of H. Instead of H, I write this expression here. When I calculate the curl of H, this part disappears, and I have a double curl of phi H. But double curl is just a Laplacian. So here I get Laplacian of H, and on the right, I keep the same thing. So this is exactly the second equation. Laplacian of phi H equals this guy here. And the first equation is exactly the same, and it follows from the second equation here. Now I can directly apply elliptic regularity, and this is the easiest setup, because for the vector potentials, even if in this PDE I have non-constant coefficients gamma and mu, for the vector potential, I still have just a Laplace equation without coefficients. So for free here, I get phi E and phi H be in L2, in H2. Right. So what happens for the scalar potentials? Here I argue exactly as I did above. I take divergences of these two equations. Let's take the first equation, for example. I take a divergence. I get the divergence of this term here, but instead of E, I substitute this expression here. And then I will have a divergence of gamma gradient of QE equal to something else, and the something else is exactly the thing that I wrote here on the left. And exactly the same, you do it for QH. And so again, exactly as in the zero frequency case, I'm left with, in this case, two elliptic PDE with non-constant coefficients, but still I can apply the H2 regularity for those elliptic PDEs, which is granted as soon as mu and gamma are W1 infinity, since the right-hand side is in L2, again, by the regularity that you see in this argument of these divergences. So just apply elliptic regularity, you get QE and QH in H2. But then if all the potentials, the phis and the q's are in H2, their gradients and curves will be in H1, and so E and H will be in H1. And this basically proves the result. So you see that it's nothing complicated. You just take the Helmholtz decomposition, write the PDEs for the scalar and vector potentials, and apply standard elliptic regularity results. So basically, this is a rather simple technique that we will see is we will apply to also to the other examples. So let's see the C0 alpha result. So in this case, what I assume is that the coefficients are in C0 alpha and the sources are in C0 alpha. I want to obtain the solutions in C0 alpha. Note that if you recall, let me see if I can go back rather quickly. Note that these are exactly the assumptions I made here in the zero frequency case. So basically, I keep the same assumptions I made for the conductivity equation for this simple elliptic PDE. And so the strength of this result is basically saying that Maxwell doesn't add any complications. You just need to apply the Helmholtz decomposition rather in a smart way. And once you do this, Maxwell's doesn't add any regularity or difficulties for obtaining a regularity for E, because exactly with the same assumptions, you get exactly the same result. Right, so let's go back to the general case for Maxwell's. So here is the result. Let's see how one proves it. So the first setup is exactly the same as we did for H1. So we write the corresponding elliptic PDEs for the vector and scalar potentials. As above, the equations for the phis are simpler because I just have Laplacians. Here on the right, the equations for the q's are slightly more complicated because I have non-constant coefficients here. So now you will see that the game is slightly more complicated than in the H1 case, because somehow we will have to move back and forth from these two equations. Let's see how it works. So let's start from the easy ones, from the Laplacian equations here. And the first step is exactly as before. Since this right-hand side is easily in L2, you get the phis in H2 automatically by H2 regularity. And now we cannot stop there. We need to insert this assumption on the right somehow. But on the right, I do not have the phi directly, I have the curves. So what is this telling me about the curves? Well, if the potentials are in H2, it means that by Sobolev embeddings, they will be in W16. Recall that we are in 3D. and so the curves will be in L6. Right, so since the JEs are in C0 alpha and in particular in L6, it means that these two arguments of these divergences are in L6. This guy here and this guy here is in L6. They are in L6. And so we can apply W1P regularity to these PDEs here. And we can do that because mu and gamma are C0 alpha. So this is allowed. And basically, if these guys are in L6, automatically you get the gradients of the solutions. So gradient of QH and gradient of QE in L6 as well. So this is an additional step, which allows me to conclude that E and H are in L6 as well, because both the gradient of QE, the gradient of QH are in L6 thanks to this, and the curl of phi E and the curl of phi H, they are in L6 because of the first step. So now the idea is that I go back to the PDEs on the left, and since E and H are in L6, it means that these two right-hand sides are in L6, and again, this time applying W2P regularity, so not anymore W22, but W2P, I gain a little bit in the regularity of phi E and phi H because now they will be in W26. But being in W26, it means that the curves are in W16, and by Sobolev embedding, it means that the curves will be in C0 1/2. And now I go back to the right. I'm not done yet. I go back to the right and I apply Schauder estimates. Why? Because the curl of phi's will be in C0 1/2, these guys. The JM and JE will be in C0 alpha. So all these arguments will be in C0 alpha. And then I can apply the Schauder estimates because mu and gamma are C0 alpha. And so these are the minimal assumptions to apply the Schauder estimates. And this gives me the gradients, these two gradients in C0 alpha. And this is exactly what I wanted because I have both curves and both gradients here in C0 alpha. The gradients are here, the curves are here. And so basically this concludes the proof. This gives me E and H in C0 alpha. So again, the message of this slide is that once you consider the Helmholtz decomposition of the two fields, you write down the PDEs satisfied by the scalar and vector potentials, and then you just need to apply classical elliptic regularity results in a smart way. And if you do it in a smart way, then you will see that basically you can just reobtain the known results for the conductivity equation, the classical ones, exactly the same, with exactly the same assumptions. They hold also for Maxwell's equations without any additional requirements. All right, so what happens with higher regularity? Well, the main message is that since for elliptic equations we have higher regularity results, basically you just need to apply those higher regularity results to obtain higher regularity results for Maxwell's equations, because you write down the PDEs for the potentials and you apply there the higher regularity results for elliptic equations. So basically now here, I don't want to go into the details because they may become slightly technical. I'm just writing down the statements. Here, this was the H1 result. If you want an HN result here, you just need to put an N everywhere, basically. So instead of W13, you will have W1N and then you put an N everywhere. So you just increase the regularity everywhere. And since this is allowed for elliptic equations, you get it also for Maxwell's. In a completely similar way, the corresponding result for Hölder continuity, that's here, instead of having C0 alpha everywhere, you just put Cn alpha everywhere. And then basically that's it. So higher regularity, thanks to this approach, which totally relies on classical stuff for elliptic equations, doesn't create us any problems. All right, so well, perhaps I can see whether there are any questions so far, because I will move to the second part of the talk, namely how to deal with global regularity. So if there are any questions or doubts or comments, I'll be happy to answer to them. All right, so global regularity. So this is something that I repeated a few times already. What are the key points so far? the key points are, first of all, I decompose E and H with the Helmholtz decomposition. So using the scalar and the vector potentials here. And then I write the PDEs satisfied by those potentials and I apply elliptic regularity. So how do we obtain boundary regularity for Maxwell's? Well, the idea is just to use boundary elliptic regularity for these equations here, because I mean, for elliptic regularity, the boundary case is very well known, is very well studied. However, in order to obtain boundary regularity in elliptic equations, you need boundary conditions for the solutions, because without boundary conditions, of course, you don't get any boundary regularities. And so here we need boundary conditions for all the 4 potentials. So let's see what we have so far. Well, for free, the Helmholtz decomposition, if we apply it with boundary conditions, the Helmholtz decomposition gives me these 3 boundary conditions. So this is telling me that the normal component of phi E is 0, the tangential component of phi H is 0, and QE is 0 on the boundary. So these are the 3 boundary conditions I have. Here, apparently, I have many more solutions, so I have to see how to obtain all the other boundary conditions I need. So let's start from QE. Let's see whether QE I can obtain regularity up to the boundary for QE. So this was the elliptic PDE satisfied by QE. As I mentioned before, the Helmholtz decomposition gives me QE equal to 0 on the boundary. And so basically, this is the easiest thing I could hope for. This is just a Dirichlet problem for this PDE. And then boundary regularity is super easy by using elliptic techniques. So basically, there's nothing to say for QE. So QE is done. Now let's see for QH what happens. QH doesn't have, unfortunately, its own boundary condition. So what can I obtain for QH? Well, let's see. So this is one of the 2 Maxwell's equations. I take a normal trace on the boundary, and so that's what I write here. And then on the left, I expand these. I use a vector identity. I write the curl of E dot nu as the divergence of the tangential component of E. This is an easy vector identity. And this is 0 because E cross nu was 0 by assumption. So the boundary condition I put on Maxwell's equation was exactly E, the tangential component of E being 0 on the boundary. This is the so-called Dirichlet condition on E. Right, this gives me 0. Then I write H with its Helmholtz decomposition. So I decompose this term here into these 2 parts. And then I want to find some boundary condition for this term here for QH. And so I isolate this thing here from this identity. And that's exactly what I get. But then you just compare this quantity here with this one. That's exactly the same, just a Neumann condition. And this one with this one, again, is exactly the same, just a Neumann, a normal derivative on the boundary. So this means that these 2 coupled together give me just the Neumann problem for this PDE. So basically, Neumann problems means that I can take test functions not only in H10, but in the full H1. This is a great news because this completes my PDE with a Neumann boundary condition, and therefore I can apply elliptic regularity easily. So Q and E and QH are dealt with. I can obtain these Dirichlet and Neumann problems and apply classical elliptic regularity results. As I said, I don't want to go into the details of those applications. These are just the main ideas. Now let's see what happens with phi E and phi H. So phi E and phi H have these 2 PDEs and these boundary conditions. However, if we just count how many PDEs and how many conditions I have, I'm losing something here, because in this case I have 2 systems of PDEs and each system has got 3 components because these are vector fields. So here I have 6 PDEs, but I only have 3 boundary conditions because this is the normal component giving me 1 boundary condition, and this is the tangential component giving me 2 boundary conditions. So in total I have 3. So I'm missing something here. So let's see what to do, how we can somehow complement these pieces of information we have so far. So for simplicity, so far, for the moment, let me consider the flat case. So let's focus on phi H. So these are the equations for phi H. This is the PDE, and these are the boundary conditions. The tangential components are equal to 0. And flat case means that omega is, at least locally, the negative half space, so x3 less than 0. In this case, nu, namely the normal, is just E3, this vector here. So we have this condition here. This is the boundary condition. What does this mean? It means, it means that the tangential component of phi h are 0, but the tangential component, since the boundary is flat, is the horizontal plane, the tangential components are those aligned with the first and second axis. So basically I get phi h1 and phi h2 to be 0 on the boundary. Good. But then I also have, and this is just thanks to the Helmholtz decomposition, phi h is divergence free. If it's divergence free, let me just expand the divergence. And so the divergence becomes this expression here. But then phi h and phi h1 and phi h2 are 0 on the boundary. So these two guys are 0, but then they are 0 also when I differentiate them with respect to the first and second axis, because I'm still differentiating them with respect to directions that are within the plane, within the plane given by the boundary of omega. And so these two guys are 0. And so I get this thing here. But what is this? D3 is nothing but d nu, because the derivative with respect to the third axis is nothing but the normal derivative. And so what I'm left with here is just a Neumann problem for phi h3. So basically this argument is showing to us that even if I do not have full boundary conditions, in practice, the divergence-free condition gives me the additional one that I was missing. And so basically for the first two components, I have a Dirichlet problem. And for the third problem, I have a Neumann problem. So now, without going into the details, in this way, you understand that somehow I can complete this PDE with suitable boundary conditions, at least in the flat case, and then apply simple results for the elliptic equations with boundary regularity. All right, so this somehow gives me the flat case. It remains to understand how to get the non-flat case. So to get the non-flat case, it's a matter of flattening out the boundary. Here, the business is slightly more complicated because Maxwell's equations are given by a system of PDEs, which is the magnetic the electric and magnetic fields are in fact tensor fields. So the way they change, but with a change of coordinates, they are not, I mean, they're not complicated, but they're not so easy. It's not as if you had a simple elliptic scalar PDE. So let's see how this can be done. So suppose that omega is locally defined by this equation here, by this inequality here. So basically you have a situation like this one, let's say. Now the idea is to flatten out the boundary. So you make a change of coordinates and you transform the boundary into you transform the domain into the half space, exactly as we had before. This of course is done only locally. But then, you know, you use a partition of unit and blah, 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 you merge everything together. So now it's a local argument. Locally, the boundary is defined by this inequality. You flatten out the boundary and you change the coordinates to make it flat. Right, now so we have to understand the effect of this change of coordinates in the PDE. So let's see. So it's a relatively simple calculations, even though you have to write down things properly. If you are familiar with differential geometry, this will be super simple to you. For me that I'm not familiar with differential geometry, not so much at least, I still need a few minutes to write this calculation down. Anyway, you understand that if you do this change of coordinates, the new coefficients gamma and the new field E, we call them with a tildes, and they will obey the following relationships with the derivative of phi. And with these new objects, basically the old PDE, this is the original one, is transformed into this new PDE here. So basically these transformed quantities satisfy the new PDE in the new domain here. You see that instead of, I'm just focusing on E, so instead of writing the curl of H in the second equation, I'm already writing the equation after divergence is applied. So that's what's left in the second equation after a divergence is applied. Good. So what's the novelty? So what's the message here from this from this, if we compare these two PDEs, these two systems of PDEs, you see that basically you get exactly the same equations with, on the left, the original E and H in this non-smooth but not flat domain, and the new objects with gamma tilde and E tilde in a new domain here with, and that's the nice bit about it, that the tangential component of E are transformed into the tangential component of E tilde. And so the tangential component of E tilde are 0 on the boundary. But then this is exactly the case we studied in the previous slide, this slide here with the flat case. And so basically this shows that by flattening out the boundary, you change the problem into basically the same PDEs with different coefficients, but, and that's the important observation, the regularity, the important observation is to understand how gamma is transformed into a new object. And so basically how phi matters into the regularity of the problem. So let's see. So these are the new PDEs, and the coefficient here, the new coefficient is gamma tilde, which is given by this expression here. So let's see what regularity we need. So suppose that the boundary of omega is of class C11. This means that phi is of class C11, because kappa was of class C11, and so phi prime is of class C01, so phi prime is Lipschitz. But if phi prime is Lipschitz, you see automatically that if gamma is Lipschitz, also gamma tilde is Lipschitz, and so basically H1 regularity is okay, because H1 regularity needed gamma Lipschitz or gamma in W13, but this is still okay. Or C0 alpha is still okay, because if gamma is C0 alpha, then also gamma tilde is C0 alpha, because this multiplication doesn't have any effect there. Good. So basically this shows that boundary regularity can be easily dealt with by this change of coordinates and applying classical results in the elliptic case. And of course, the higher regularity results are obtained in a similar way. If you increase the regularity of the boundary of omega, you increase the regularity of kappa, but then you increase also the regularity of phi, and then you increase the regularity of phi prime. And so basically, if gamma is more regular and phi prime is more regular, also gamma tilde will be more regular. And so we are able to apply higher regularity results for this elliptic PDE. Right, let me mention that these types of arguments here apply only if the domain is smooth. So basically, if I can actually make a smooth change of coordinates, make a transformation of the domain, use the flat domain, and do the calculations I showed you. In the case if the domain is non-smooth, then particular and interesting phenomena do appear. And so basically, there are singularities that appear. There are many results on this topic which are relevant, as you can imagine, also for like the numerical analysis for these problems, because as soon as you have domains with corners, you have to understand how the solutions behave near those corners in order to solve them efficiently using finite elements, for example. But I'm afraid this would make this talk much more, well, it would be another talk. So I cannot mention anything on these things. If you're interested, you can either look at those references or let me know, and I'm happy to point toward to give you references on these topics. All right, so I think I have more or less a few minutes left. Let me mention what can be done in addition to this, because so far we just saw interior and global regularity results for either H1 or C0 alpha estimates, possibly also with higher regularity. However, the interesting thing is that this type of approach, since it reduces completely to the elliptic case, allows one to actually explore other directions and obtain other regularity results. For example, the first one is again on the Hölder class, but in this case, we require only gamma to be regular. So basically one of the two coefficients to be regular. In this case, you get only one solution to be regular. So basically, since gamma was next to E, then if gamma is regular, you get irregular. So in other words, you do not need both gamma and mu to be regular if you only need E to be regular. It's enough for one of them to be good, and also and so the corresponding solution will be okay as well. So basically, you do not need joint regularity for gamma and mu. Only one of them is enough. If you are happy with a partial regularity for the solution, in this case, only on E. Of course, there is the corresponding result. If you require regularity only on mu, you get regularity only of H here, exactly the symmetric case. Then you can, instead of considering only H1 type regularity, so basically with P equals 2, we can think about results with general P, and these are obtained in a similar way as the approach I discussed in this paper. The only complication is that you need to use much more the W1P regularity for elliptic equations, which is developed but not so standard. I mentioned something with the L6 regularity for proving the C0 alpha estimates during this argument, during the talk. Here it's gonna be it would be similar type of reasoning, and basically you get exactly the same result. So if you have coefficients in W1P, you get solutions in W1P. Right. Note that you cannot go below 3. So below 3, this is not true anymore. So for 2, for example, you cannot, at least as far as I know, you cannot take the coefficients in W1, 2 and obtain the solutions in H1. This is not possible. One additional thing is Meyer's theorem. You may be familiar with the fact that with elliptic equations, you have an elliptic equation, say the conductivity equation, so divergence of U of sigma grad Q equal to something. And this in principle is only in H1. And being in H1 means that the gradient is in principle only in L2. This is the standard weak formulation of elliptic PDEs. However, the nice thing about this Meyer's theorem is that without assuming any additional regularity on sigma, so sigma is just L infinity, the solution Q is not only in H1, so the gradient is not only in L2, but actually is in a little bit more than L2. So this is the so-called higher integrability for elliptic equations, and the gradient is actually in L2 plus delta. And well, exactly the same theorem can be proven also for Maxwell's equations without any additional assumptions, and basically you get the solutions not only in L2, but in a little bit more than L2. You get them in L2 plus delta. And the proof goes exactly as I discussed in this talk. So you write the Helmholtz decompositions, you write the elliptic PDEs for the potentials, and you apply Meyer's theorem for the elliptic PDEs for the potentials. So basically, again, the message is if it's true for the elliptic PDE, then it will be true for Maxwell's as well. And finally, this is something that it's related to regularity. It's not exactly the same as regularity, because this is actually not regularity, meaning that what happens if you actually have a coefficient gamma, let's say, that is not smooth, so it's not C0 alpha, for example. It's not continuous, your gamma, but it has a singularity, it has a discontinuity, say, in one ball. So what happens if your gamma has a discontinuity in one ball, so there is a small inclusion? This is relevant, for example, for homogenization or inverse problems. Well, what happens is that the solution E will fill this singularity, and you may want to understand what's the first order effect of E with respect to this singularity. This theory is very well developed for the elliptic case. And so basically what we can show is that by applying, again, the same type of ideas used in the elliptic case, using the Helmholtz decomposition, you can write the same asymptotic expansions also for Maxwell's equations. All right, I think I have 1 minute. And so basically this is the end of my talk. And I hope that I convinced you that Maxwell regularity is nothing but Helmholtz decomposition plus elliptic regularity. So basically this means that as far as regularity is concerned, if you take Maxwell's equations and you want to understand how regular the solutions are, you do not have to develop a theory ad hoc for Maxwell's equations that could be complicated. The easiest thing you can do is to use properly the Helmholtz decomposition, write the potential, the E and H with the scalar and vector potentials with the Helmholtz decompositions, and then you write down the PDEs satisfied by those potentials. They will be elliptic PDEs, and then you just apply elliptic regularity to those PDEs. And this for free will give you the corresponding results for Maxwell's equations as well. All right, thank you very much. I'm done.
Thank you very much.
Thank you.
So let's move on to questions. So any questions for the speaker?
Could I ask a question? I'd like to check that I understand correctly one of the consequences of these other results you were mentioning at the end. So it seems that if you had a Maxwell system with, let's say, smooth coefficients, including smooth conductivity, and then you perturbed the conductivity so that it became non-smooth, then the effects in the regularity, according to what you were saying at the end, would only be felt in the electric field and not in the magnetic field. Is that correct?
No, it's at first order. Yes, it's felt. You feel it only in E, but somehow this, if you look at this equation, this term here, this implication here, holds only for 0. You cannot put a higher regularity result. So if gamma is C infinity and mu is L infinity, it doesn't mean that E is C infinity. And the reason is that as I showed you before, to prove this theorem, you have to go back and forth from the PDs for E and for H, for the scalar potentials and for the vector potentials. So you cannot focus only on one bit. You have to move from E and H and from the vector and from the scalar potentials. So somehow you cannot get C infinity. No, that's not possible.
Okay, so the more correct statement would be that at the leading order, you would see the effects in E, but you would still see also the effects on the magnetic field and in the electric field, but also, obviously, but in the magnetic field in the higher orders.
Yes, exactly. So at first order, you wouldn't see it. And when I say first order, I mean in first order with respect to the size of the perturbation. So if the size of perturbation is of order epsilon, then at order epsilon, you see it only in E, but then at order epsilon squared, you see it also in H.
So this also, I mean, I guess means that if, for example, one is trying to solve an inverse problem associated with Maxwell, then depending on which coefficients you're most interested in recovering, you would be better to measure either electric or magnetic field on the boundary more precisely.
Yes. Well, the thing is that if you measure it on the boundary, then you would still have an infinitely smoothing effect away from the singularity, because somehow this,
Sure.
So we are talking about an infinitely smoothing effect versus a first order effect. So you would still be in serious troubles. If you, on the other hand, have interior measurements, then if you can measure here on H internally, then certainly if you measure E, you'd better recover gamma instead of mu, because it's gamma multiplied by E, so you feel it immediately.
Thanks.
Yeah.
So more questions.
Can I ask something?
Please go ahead.
So in this slide, this result about the W1P regularity. It seems to me that you need to require this P greater than 3 in order to apply this classical W1P regularity result. Is it correct? Or because I was wondering if you could reach P equal to 3 basically, so that you would have the critical embedding for the Sobolev embedding theorem.
So I looked into these questions a few years back now, so they're not so fresh in my mind anymore. There was a time where I tried to look into optimal regularity, and then I gave up in this setup. For the C0 alpha, this is optimal. I forgot to mention it. but in the PK, in the W1 P case, it's more complicated. I think it's more complicated than only the W1P regularity. Because for W13, if I remember well, W13 would be in VMO, and VMO still allows for applying the LP regularity for elliptic equations. So the P equal to 3 case is still okay for that bit. So for the LP regularity for elliptic equations is still okay. The problem is that W13, I don't remember, doesn't allow you to bootstrap in some because you need to do a bootstrap argument here, and possibly the P equal to 3 case keeps you blocked somehow. But I'm afraid I do not recall the precise detail of this.
All right, thank you anyway.
Yeah.
Further questions? If not, maybe I'll ask something about these inhomogeneities that you were mentioning at the very last. So suppose you have some sort of inhomogeneity with, say, a Lipschitz boundary, and you have, say, constant coefficients inside and constant coefficients outside, just for simplicity. Would Lipschitz boundary be enough to get any decent regularity for solutions, or at the interface, or would you need something better than Lipschitz?
The thing is that in this case, now I wrote this a few years ago, so I do not recall the precise assumptions. What I could say here is that in this scenario, we do not study the regularity of E somehow. We study the expansion of E with respect to, so basically we study E, we write E as a first order expansion, which is the electric field if there was no inclusion, so without the inclusion, plus a term that is small in epsilon, okay? So this term that is small in epsilon, you can still write it in this setup here, even if the boundary is Lipschitz. So this doesn't create a problem. However, note that somehow this boundary moves with epsilon. So the correction, the term that you have to correct will certainly have some problems along the boundary. There's nothing you can. This is unavoidable. Because if you have a jump in gamma, you will have a jump in E. This is something that you cannot avoid.
I see. So it's more in the spirit of homogenization expansions rather than fixed size defects.
Rather than, sorry, I missed that.
Fixed size defects.
Yes, absolutely. Okay. Yes. Yeah.
Okay, thanks. Are there any further questions for Giovanni in the audience? If not, let's thank him again for the really excellent talk.
Thank you. Thank you.